All right, we're going to do our first video here on analytic trigonometry. This is section 14.3, verifying trigonometric identities. And this is kind of our first look into this branch of trigonometry where we're using these things called identities to simplify, prove things, and solve equations. So the first identity we're going to look at is known as a Pythagorean identity, and it's based off of the unit circle and the Pythagorean theorem. We know that on the unit circle, given any point, and I have x, y here, but what we know from past units in trigonometry is that that point really does represent the cosine of whatever this angle theta is, and the sine of whatever that angle theta is. So really, this x value is the cosine of theta, and this y value is the sine of theta. Because we're dealing with the unit circle, we know that it has a radius of 1. So using that right triangle and using the Pythagorean theorem, we can write, instead of x squared plus y squared equals 1, because the radius again is 1, but that the cosine squared of theta plus the sine squared of theta would equal 1. And know that I'll just use this one as an example. This really means the sine of theta squared. Is just faster for us to write it with the 2 in between the function and the angle. And then I have here, we can prove that this works just for one of our angles that we know, pi over 6. We know that the cosine of pi over 6 is square root of 3 over 2. So if we use this definition here, we would have the square root of 3 over 2 squared. There's cosine squared plus sine of pi over 6 is 1/2 squared. We can prove that this equals 1 by squaring each of these and then adding them together. We just prove that it works for that one angle, pi over 6. But really, this would work for any angle, and that's why we call this thing an identity. These statements that work for any theta are known as trigonometric identities, and they are equations that are true for all angles of theta as long as it is a defined value in the domain of that function. So here are what are known as the Pythagorean identities. The first is cosine squared plus sine squared equals 1. And again, this is the one that we listed up above, but I just point out here that because this is addition, this is commutative, you can flip that around and say that sine squared plus cosine squared equals 1, same thing. To get the other two main Pythagorean identities, what we do is we take that equation and we can divide it either by sine squared or cosine squared. Let's first divide it by sine squared. So in red there I have by cosine squared first. In red I have what this would become if we divide it by cosine squared, each term. So cosine squared divided by cosine squared is 1. Sine squared over cosine squared is tangent squared, because sine over cosine is tangent. And 1 over cosine squared, 1 over cosine is secant. So that gives us secant squared. If we start with that original function again and divide by sine squared, we get cotangent squared plus 1 equals cosecant squared. These are the three Pythagorean identities. Okay, we're not asking you to memorize all these, just that one. I think that one's pretty easy to memorize. It just uses cosine and sine, and I think it's pretty easy to remember that cosine squared plus sine squared equals 1. And then you need to know how to get to the other two by dividing by cosine squared and sine squared. When we do that, we're actually using other identities as well. Identities that you've known for weeks, just we've never had these down on paper actually, or we've never actually called them identities. We've had these in some of our notes before. The fact that we have three reciprocal functions, cosecant, secant, and cotangent, and there we are defining them as reciprocals of the three major functions, sine, cosine, and tangent. And then what are known as the tangent and cotangent identities. The tangent is sine over cosine. Cotangent is cosine over sine. We've known those. We've used those ideas before, but now we're going to be using them in a little bit different way. So these are the three Pythagorean identities. I have them written down here again, and the reason why I did that, up here I'm showing you how we come up with all three. You know, the first one is one that you got to memorize, that one that's in black, and then the red and blue you need to know how to get to. What we're going to do down here is rewrite these in a couple of different ways, just so you can see these in other ways, because that's essentially what we want to be able to do in this section is visualize these identities rewritten in other forms. For example, the main one could be written in terms of or being solved for cosine squared. We could say that cosine squared would equal 1 minus sine squared. We could also solve this for sine squared and say that sine squared equaled, if I subtract that, cosine squared over 1 minus cosine squared. Okay, so those are just two of the ways that we might be using these functions. We can do the same thing with the other two. We could have the value of 1 all by itself in this one and say that it's secant squared minus tangent squared. We could have the value of tangent squared by itself and say that tangent squared equals secant squared minus 1. I'm just doing a little bit of algebraic, moving things around here. And then finally, with our last one here, I could rewrite this one in these two ways and having cotangent all by itself. Cotangent squared would be cosecant squared minus 1. And I have you do that on this sheet here so that you just see these in other ways. As these portions pop up in other problems, hopefully you'll recognize basically when you see something squared, a trig function squared, or if you see a 1 minus something squared, we are going to be probably using a Pythagorean identity, okay, in some way, shape, or form. All right, the cofunction identities. I'm going to give you a second. Actually, I'm going to give you a second if you want to pause the video to write both the cofunction identities and the odd and even identities down. We've used these ideas before. Basically, the cofunction identities tell us that the sine and cosine of two complementary angles are equal, or that the tangent and cotangent of two complementary angles are equal. And the odd even identities are telling us that the sine of a negative angle is the same as the opposite of the sine of the positive angle, where the cosine of a negative angle is the same as just the cosine of that same angle. For example, you don't have to write this on your notes, but the cosine of negative 30 degrees would be the same as the cosine of 30 degrees, because negative 30 is in the fourth quadrant, 30 is in the first quadrant. Obviously, they both have the same reference angle, but cosine is positive in both spots there. So that's an example of why there's no negative right there. With sine, if we did the sine of negative 30, well, we know the sine of negative 30 is negative. Sine is negative down there. So that would be negative 1/2, for example. That wouldn't equal the sine of 30. It would equal the opposite of the sine of 30. So we can see why that one is true as well. So take a moment, pause the video, and write those down. And we'll start using these to do a couple different types of problems here. All right, the first thing we're going to use the identities for is to evaluate if trig functions given a trig function. Basically, if you're given one trig function, instead of drawing a triangle, which we've done this in the past, we've done this using right triangles, we'd like you to stick away from that now and completely use these identities. What we can do is find other trig functions using the Pythagorean identities. So in these evaluating problems, we're going to almost exclusively be using the Pythagorean identities. So we're given sine. So in fact, I'm going to write that down here. Sine is 4/5. And we're going to look for the other 5. Well, cosecant's going to be pretty easy to come up with because we know that cosecant is the reciprocal of sine. In fact, that was one of our identities from up above, that cosecant is the reciprocal of sine. The other thing I'd like you to notice that we are told what quadrant our angle is in. We are in quadrant 2 here. So in quadrant 2, we know that sine is positive, which makes sense that the 4/5 is given to us as a positive value. But cosine and secant are going to be negative, as well as tangent and cotangent. So I'm just going to get that out of the way right away. We want to find another trig function here. So if we have sine, the easiest thing for us to find is cosine. If you're looking at this already going, I know what these values are, this is a Pythagorean triple, that's good. We're using some easy numbers to show you this process. Example 2 is going to get dramatically harder, but we thought we'd start small here. We'd still like you to use the Pythagorean identities just to show that you know how to work with them. So we're going to take 1 minus sine, which is 4/5 squared. Be careful not to write the sine of 4/5 right there. The sine of theta is 4/5, so we replace sine of theta with 4/5. So this is 1 minus 16/25, or 9/25, since 1 is 25/25. And we still need to take that square root here. We have 3/5. For cosine, we know it's negative. We already took care of that. But had you not taken care of that, this would be the spot where you take the square root. You know, we usually think about that positive negative thing here. That's a spot where you got to go, oh, what quadrant am I in? Should this be positive or should it be negative? Obviously, this one should be negative. We'll flip it to get secant. And then we'll use the tangent identity of sine over cosine to get our last two values there. And then we'll flip it to get cotangent. All right, let's do this next one with cosecant being -8. So let's put that down here as a given value right away. Cosecant is -8, which would make sine -1/8. We are in quadrant 3, which means that both sine and cosine are negative, and tangent and cotangent will be positive. We're given cosecant. If you look at your Pythagorean identities, the one that has cosecant in it is right there, and you can use any form. You know, here's the main function, and we can use any form of that. Well, if we have cosecant, we can use it to find cotangent. So basically, the idea we want to be using is that one right there. And we can find cotangent squared, because we know that it's equal to cosecant squared minus 1. Cosecant is -8. So we have 63 here. That cotangent squared is 63, 64 minus 1. And that cotangent itself would be the square root of 63. 63 can be broken down into 9 and 7, so that would give us 3 square roots of 7. So that's the cotangent value, 3 square roots of 7. Now if we reflect that, excuse me, not reflect it, I don't know why I keep saying that. If we find the reciprocal of that, 1 over 3 square root of 7, that's our tangent value. We'd have to rationalize by multiplying by the square root of 7. And that would give us the square root of 7 over 3 times 7, which is 21. A couple different things that you could do here. You could use a Pythagorean identity again to find cosine, if you know that sine is 1/8. You could also say that you know tangent, which is the square root of 7 over 21, is equal to sine over cosine, and you could use that in order to find cosine. Let's just go with the fact that, oh, I don't know, I'm going to go outside the box here and say that cotangent is equal to cosine over sine. Therefore, I know that cosine equals cotangent times sine, because I have those two values. I have cotangent, it's 3 square roots of 7. I have sine, it's -1/8. So that would be 3 square roots of 7 over 8, or -3 square roots of 7 over 8. And we could reflect that. I said it again. We could flip that, find the reciprocal of that, in order to get secant. Do a little rationalizing here. We'll have 8 square roots of 7 over 3 times 7, which is the 21 again. So that is evaluating. Okay, I think this is a good time to break this section up. So we'll end this first video here, and we'll do our second video on simplifying and evaluating.